here we're going to look at even and odd functions. So we're just going to start by getting some definitions out of the way, and then those won't be super clear right now, but I'll go into some examples and make that a little bit clearer. So let's just say a function is even. Even is the definition here that we're going after. If f of negative x, that's saying that we just plug in negative x into the f function, all right? If we plug that in and we do some simplifying, and it equals the original function, f of x. So what that's saying is we take a negative x and we plug it into our f function. And after we simplify, if we wind up with our original function after we get done simplifying, then that's an even function. That means none of the signs would have changed. So just some subnotes here. No signs change. That will be a key part here in a little bit. And then another key part is if it's an even function, it's symmetric about the y-axis. So that gives us a visual representation of what an even function is going to do for us. The second one is an odd function. A function is odd, that's the definition I'm going for here, if f of negative x, so it starts out the same, you're still plugging in negative x into your function, then you're going to do some simplifying. And then what you get when you get done simplifying is negative of the original function. So if it's negative of the original function, that means all the signs change here. All signs change. And another helpful thing we need is it's symmetric about the origin. All right, so those are our two big ones there. And just to note, you could have a mixture. So you can have some of the signs that change and some of the signs that don't change. You can have a neither function also. It just means some signs change, some don't. All right. Some examples will help make some of this a little clearer, and then we'll get into what this f of negative x looks like, how we simplify a problem. So let's see. Let's try example 1. Determine if the following are even, odd, or neither. And here is part A. We're going to start with a graph. I think this will help us see part of this. X-axis, y-axis. And in my graph, we're going to have something like this. And this is the f of x equals x squared function. All right, so what we're going for here is we want to determine if this graph is even, odd, or neither. So based on the rules the definitions I just wrote, this is symmetric about the y-axis. So if you take your hand and you flip it over the y-axis, is it a mirror? Do they mirror each other? Yes, they do. When you flip it over, this point becomes this point. So just by looking at it, you can determine that this is an even function. All right? What it means to be even is if I take, say, this value of negative 1 here, I get this value of 1 right there. So when I plug in negative 1, I get 1. Excuse me, I'm sorry. I'm plugging in 1, not negative 1, sorry. When I plug in negative 1, I get this value of 1. All right? What happens when I plug in negative 1 into the x squared function? So let's just do it real quick. Let's start back at 1. So x equal 1 means I plug 1 in here. 1 squared is 1. Now let's plug in negative 1. If I plug in negative 1 squared, I also get 1. So I get back the same answer, or the original answer. And that's true for 2 and negative 2 and so on. These answers here are the same. So that's what it means to be an even. You plug in the positive or the negative and you get the same output, or the same y value. That's what it means to be even. That's why we're plugging in that negative value. That's why we're saying f of negative x is equal to f of x. We take our normal x values, and then if we plug in a negative of that value, those outputs should be the same. That's what it means to be, that's why we're doing f of negative x. So part B, let's look at doing it, or working it out by hand. So I want to determine, if I didn't give you the graph, and these are going to get much more complicated and longer, where you won't necessarily be able to graph them just offhand. But just as good practice, let's just treat this as all I gave you was this function, and you need to show your work and determine if it's even, odd, or neither. So the way all of these work, whether they're going to be even, odd, or neither, they always work the same. You always start by plugging in negative x. So f of negative x. That tells me I'm using the f function, and I'm plugging negative x in there everywhere x occurs. So here's my only x, so that becomes negative x squared. You have to use parentheses there. All right, now we want to simplify this. And what I mean by simplify is we can multiply this thing out to potentially get rid of that negative term. So let's work it out. So negative x squared, that means I'm multiplying negative x times itself twice. So I can rewrite it as negative x times negative x. A negative times a negative is a positive, so the negatives go away. They get eaten away. And then I'm left with two x's that are multiplying to each other, so I get x squared, which is the original function, f of x, which is equal to f of x. So what happened was, I plugged in negative x, and then I did some simplifying, and out popped the original function. So you just need to compare and see if the signs changed here, and they didn't. So that means it's an even function. And these are going to continue to get longer, these problems. So the key here on an even function, let's look at one more example of before I tell you the little hint. C, let's call it g of x is equal to x to the fourth. All right, I want to know if this is even, odd, or neither. So how does it start? It starts the same way every single time. Plug in negative x. That means I'm taking negative x and I'm plugging it into my g function everywhere there's an x. So this becomes negative x to the fourth. And then let's expand this out and multiply and simplify it. So negative x to the fourth means I'm multiplying negative x times itself 4 times. negative x times negative x times negative x times negative x. Now let's simplify it. So negative times a negative is a positive, and then a positive times a negative is a negative, then a negative times a negative is a positive. So multiplying these four negatives together winds up with a positive. And then I have four x's here that are multiplying together, which gives me x to the fourth. And notice that this is the same as the original function. None of the signs changed. So that's equal to g of x. All right? So what do you notice here between b and c? Their exponents are, that's a 2 over here, and this is a 4 exponent here. What do you notice when the exponent is even? That negative you plug in gets eaten away. It just goes away. And I showed you why it goes away right here with these steps. So think of even exponent, the negative gets eaten away. Even and eaten, they're both e's. So even exponent, it eats away that negative. All right? Now let's look at part D. And let's call it h of x is equal to x cubed. No, I'm sorry. I just spoiled it. I'm going to look at the graph first. Here's the x-axis and the y-axis. And then the graph looks something like this. Best of my ability. Okay, so just by looking at this graph and looking and going back to reread the definitions that we wrote at the beginning, we know it's an even function if it's symmetric about the y-axis, which this clearly isn't. If you take this and reflect it over here, it doesn't look like it. But it's an odd function if it's symmetric about the origin. So here's the origin. So there's two different ways to look at this one. You can, if you have your hand here and you rotate it 180 degrees, does it match up? And it does. You take this and you move over here and they look exactly the same. Or you can view it as it's reflected. Does it look the same if you reflect it across the y and then the x? So you take it here and you move your hand here and then here and it looks the same. So if you were to reflect it across the y, it would look something like that. And then if you were to take this and reflect it across the x, they would perfectly match up. So that's kind of what it means to be symmetric about the origin. Just think of it rotating 180 degrees like this, or two quadrants. So just by looking at this, you can see it's an odd function. Now let's get into what the negative, when we plug in negative x, what that means. So let's say we have this 1 here, x equals 1, and when you plug that in, oh yeah, I need to write. Gotta get in the habit of labeling everything. So the graph is h of x equals x cubed. So if I were to plug 1 into this function, so 1 cubed, that's just 1. So that gives me the value of 1 right there for y. Now let's say I plug in negative 1. That gives me this value here, which is negative 1. So what's happening is I take the original function, or I take the positive, I should say, x, and I plug it in and I get the positive of the 1. But if I plug in the negative 1, I get negative 1, or it's the negative. So relating it to the previous examples and plugging in negative x, if I have 1, I get the positive of 1. I get the same thing. If I plug in the negative of my x value, it changes. It's not the same y value as before. All right, so looking at it from this perspective, h of x is equal to x cubed. It starts out the same. We plug in negative x into the function, and we do our simplifying. H of negative x. So just plugging in our negative x. Again, it works exactly the same way every time. After this point is where it starts getting a little different. So just to show you what happens here, negative x cubed means multiplying itself negative x 3 times. Negative x times negative x times negative x. And what happens to those negative terms? They, negative times a negative is a positive, and a positive times a negative, negative times negative is a positive, positive times negative is a negative, and then you have these three x's that are multiplying, which makes x cubed. So what happens is, you compare this to the original function, and the sign's changed. So that means it's an odd function, or it's equal to the negative of the original. So this is odd. So what these boil down to is, when you plug in negative x, you look at the exponent, and if it's an even, like the previous examples, that even exponent eats that negative away and it just disappears. But if you have an odd exponent, like we do here, it takes that negative and it moves it to the front of that term. It moves it outside of those parentheses. All right, let's look at a little bit longer of an example. That was E, here's F. Let's call this M. 3x to the 7th plus 4x cubed minus 2x. So some of you can view this already and you can tell me what the answer is, and that's great. You can see that this has an odd exponent, this term has an odd exponent, and this term has an odd exponent. If all the exponents are odd, it's an odd function. But still, you're going to want to work through it and get some practice here. So you plug in negative x, so you get 3 times negative x to the 7th plus 4 times negative x cubed minus, I messed up here. So let's erase, start that term over. 4 times negative x cubed. You have to make sure that negative x is in parentheses, and then you have it raised to that power. Minus 2 times negative x. All right, and if you're still uncomfortable with the even and odd exponent things, how we talked about it, then take one of the smaller exponents like this negative x cubed and do a little side work, and you can show yourself that it does just move that negative out to the front of that term. All right, so I know if it's an even exponent, it eats the negative and it goes away. If it's a positive, and if it's an odd exponent, it takes that negative and moves it to the front of this term. So here I have 3, and then that's times negative x to the 7th power. So this is an odd, so that negative stays and moves to the front of this term, or the front of that 3. So you just write it as negative 3x to the 7th. And that's the same way I work with all odd exponents. So you have an odd exponent, this negative moves to the front of that term, negative 4x cubed. And I say moves to the front, it changes the sign of that term. So here we have a negative x with the exponent's 1, we just don't write it, so that's odd. So that negative moves out to the front of that term and changes the sign. So if it's a negative, then it becomes a positive. And if it's a positive, it becomes a negative, just like these did. So what you do is you compare this to the original function. Did this sign change? Yes. Did this sign change? Yes. Did this sign change? Yes. So that makes this an odd function. And it works similar for even. Even's pretty easy.